We wish to compute the double integral seen here, integral 0 to 1, integral x squared to 1 of square root of sine of y times sine y dy dx by changing the order of integration. So why is that necessary? If we didn't change the order of integration, we would need to integrate the square root of y times sine y dy, and anti-differentiating that is not a simple matter. So we will change the order of integration and see if that changes our luck. In order to change the order of integration, we have to understand the region that is described by these endpoints. So we have y is going from x squared to 1. So we should draw those two curves, y equals x squared. That's a parabola. And y equals 1, a horizontal line. And x goes from 0 to 1. This is the point 1, 1. And x goes from 0 to 1. So x goes between 0 and 1. Y goes from the parabola to the line. So it's this region. So we have this region. This is y equals x squared. And this is y equals 1. And this is the x-axis. X is going from 0 to 1. All right, so this double integral can be rewritten as square root of y sine y dx dy. So y is going to go from 0 to 1, and x is going to go for any y from 0 to the parabola. And in terms of x, the parabola is x equals the positive square root of y. Okay, so there we have switched the order of integration. We have new boundaries, thanks to our ability to determine the region from the boundaries. And now we integrate with respect to x. So this integrand is just constant with respect to x. And so we can integrate it, yielding x times the square root of y, x times the constant, square root of y sine y. And then we have to plug in, for x, we have to plug in 0, which will give us 0. And we have to plug in the square root of y. And then we have to take the result of that and then try to integrate dy. So we get the integral from 0 to 1. When we plug in the square root of y for x, we multiply that by itself, and that gives us y. And we have sine y. And then when we plug in 0 for x, we get 0. So this is the entire integrand, dy. Okay, now to integrate this, which is similar to this one, but that square root makes a big difference, we can use integration by parts just one time here, and we can anti-differentiate this. So the integration by parts formula says the integral of u dv is equal to uv minus the integral of v du. So in this particular case, we're going to choose u to be y, and dv is then sine of y dy, and then we compute du. Du is 1 dy, or just dy. We compute v by anti-differentiating the sign, giving us negative cosine of y. So now we want to integrate y sine y, and I'll do that without the bounds first to get an antiderivative, and then we'll put that antiderivative here and use the bounds and get our numerical answer. So the integral of y sine y, according to integration by parts, is uv. Uv is negative y cosine y minus the integral of v times du. V times du is negative cosine y dy. So negative cosine y, and we had a minus here, so the two negatives just make a plus, and the integral of cosine is sine. So our antiderivative is negative, let's put this in blue, negative y cosine of y plus sine y. and we want to plug in the numbers 1 and 0 now for y. When we plug in 0 for y, we'll get a 0 in the first term, and the sign of 0 is also 0. So we'll get a 0, and so the answer is obtained by just plugging in the 1. So negative 1 cosine 1 plus sine 1. So the answer is sine of 1 radian minus cosine of 1 radian.